Hi, hello everyone. Thanks for joining me in my today's video presentation. My name is Pravinal. I'm a student at Sri Venkateshwara College of Engineering, Bangalore, currently studying in 6th semester. In today's video presentation, we are going to be studying on the topic 2D transformation in computer graphics. So, let's get started. What is 2D transformation? Transformation are the operations applied to a geometric description of an object to change its position, orientation, or size are called geometric transformation. So let us know more. Translation. What is translation? Translation is the process of changing the position of an object in a straight line path from one coordinate location to another. We can translate a two-dimensional point by adding translation distances tx and ty. Suppose the original position is x comma y, then the new position is x dash comma y dash. Here x dash is equal to x plus tx and y dash is equal to y plus ty. This is an example of translation. As you can see, the point p of x comma y has moved to the point p dash x dash comma y dash, where the ty and tx are the translation distances. Matrix form of the equation x dash is equal to x plus tx and y dash is equal to y plus ty is given below. P is x comma y, P dash is x dash comma y dash, and T is the translation distances Tx comma Ty. This can also be written as P dash is equal to P plus T. Now let us consider an example. The example says translate a polygon with coordinates A 2, 5, B 7, 10 and C 10, 2 by 3 units in x direction and 4 units in y direction. We can clearly see that 3 units in x direction means Tx and 4 units in y direction means Ty. So that makes us, we can write the equations for A, B, C as follows. A dash is equal to A plus T, where the coordinates are for A are 2, 5 and T are 3, 4, which makes A dash is equal to 5, 9. Similarly for B dash, B is equal to 7, 10 and T is equal to 3, 4, which makes us B dash is equal to 10, 14. And lastly, for C dash is equal to C plus T, C is 10, 2, T is 3, 4, which makes C dash is equal to 13, 7. Now we have rotation. What is rotation? Rotation. A two-dimensional rotation is applied to an object by repositioning it along a circular path in the xy plane. Using standard trigonometric equation, we can express the transform coordinates in terms of theta and phi as x dash is equal to r cos phi plus theta is equal to r cos theta cos phi minus r sin phi sin theta. Y dash is equal to r sin phi plus theta is equal to r cos phi sin theta plus r sin phi cos theta. The original coordinates of the point is x is equal to r cos phi, y is equal to r sin phi. We can see a graphical representation of rotation. Now, after substituting equation 2 in equation 1, we get x dash is equal to x cos theta minus y sin theta, y dash is equal to x sin theta plus y cos theta. Now, here is another example of rotation. As you can see, the block has rotated few coordinates from its original position compared to the first diagram to the second. Moving on, we have scaling. A scaling transformation changes the size of an object. This operation can be carried out for polygons by multiplying the coordinate values x, y for each vertex by scaling factors sx and sy to produce the transformed coordinates x dash, y dash. X dash is equal to x into sx, y dash is equal to y into sy. In the matrix form, x dash comma y dash is equal to x comma y, where the matrix 2 by 2 is given Sx0, 0xy, which can also be written as P into S. Here is an example of scaling. Scaling are of two types, uniform scaling and ununiform scaling. And in uniform scaling, the gradual decrease of the object is gradual, whereas in ununiform scaling, the decrease of the object size is non-uniform. Moving on, homogeneous coordinates for translation. The homogeneous coordinates for translation are given as a 3 by 3 matrix where 1 0 0 0 1 0 tx ty 1 in the matrix form. Therefore, we have x dash y dash 1 can be given as x plus tx, y plus ty 1. Moving on, homogeneous coordinates for rotation. The homogeneous coordinates for rotation are given as r is equal to a 3 by 3 matrix form that is represented as cos theta sin theta 0 minus sin theta cos theta 0 0 0 1. Therefore, we have x dash y dash 1, which is x comma y multiplying the 3 by 3 matrix of cos theta sin theta 0 minus sin theta cos theta 0 0 0 1, which finally gives us x cos theta minus y sin theta, comma x sin theta plus y cos theta and 1. Homogeneous coordinates for scaling. The homogeneous coordinates for scaling are given as a 3 by 3 matrix where S is equal to Sx00, 0 Sy0, 0 0 1. Therefore, the x dash y dash 1 is x comma y comma 1, which is multiplied with a 3 by 3 matrix x dash 0 0 0 xy 0 0 0 1, which is x comma y comma 1 into s, which gives us x dot ss, y dot sy, and 1. Moving on to the next topic, composite transformation. There are three types of composite transformation. The first one is translations, rotations, and scaling. So, let's see the first one, translations. If two successive translations vector tx1, ty1 and tx2, ty2 are applied to a coordinate position p, the final transferred location p dash is calculated as p dash is equal to t into t of x2, t of y2 into flower bracket t of tx1, ty1 into p. That gives us t of tx2 into ty2 into t of t1 tx1 into ty1 into p, where p and p dash are represented as homogeneous coordinate column vectors. We can verify this result by calculating the matrix product for the two associative groupings. Also, the composite transformation matrix for the sequence of transformation is given as T of tx2, ty2 into T into tx1 into ty1 is equal to T of tx1 plus tx2, ty1 plus ty2, which demonstrate the two successive translations are additive. Rotation. Two successive rotation applied to a point P produced are P produced the transform position. P dash is equal to R theta 2 into R theta 1 dot P, and which gives us R theta 2 into theta R theta 1 into P. By multiplication of two rotation matrices, we can verify that two successive rotation are additive. R theta 2 into R theta 1 is equal to R into theta 1 plus theta 2. So, the final rotated coordinates can be calculated with the composite rotation matrix as P dash is equal to R theta 1 plus theta 2 into P. Moving on to the last composite transformation, scaling. Concatenating transformation matrices for two successive scaling operation produces the following composite scaling matrices. There are three 3 by 3 matrices which can be written as S into XX2 into comma xy2 into S into sx1 into xy1 is equal to S into sx1 into xs2 comma x s into y1 into xy2. The resulting matrix in this case indicates the successive scaling operations are multiplicative. Now we have the topic general pivot point rotation. It says translate the object so that the pivot position is moved to the coordinates origin. Rotate the object about the coordinate origin. Translate object so that the pivot point is returns to its original position. We have four diagrams. Now let us see them. In diagram A, we can see the original position of an object and pivot point is x, y. Now, in diagram B, we can see translation of object so that the pivot point is xr, yr is at origin. Rotation was about, in diagram C, we can see that rotation was about in the origin. In diagram D, we can see that translation of the object so that the pivot point is returned to its position x of r dash, y of r dash. Moving on, we have general fixed point scaling. It says translate object so that the fixed point coincides with the coordinate origin. Scale the object with respect to the coordinates origin. Use the inverse translation of step 1 to return the object to its original position. Let us see diagram A which says original position of the object and a fixed point is x, r dash, x, r, y, r. In diagram B, we can see that translation of an object so that the fixed point x, r, y, r is at the origin. In diagram C, we can see that scaling was done about in the origin. In diagram D, we can see that translation of the object so that the fixed point is returns to its position x, r dash, y, r dash. Moving on, we have other transformations. From that, we have reflection. Reflection is a transformation that produces a mirror image of an object. It is obtained by rotating the objects by 180 degree about the reflection axis. There's an example given below. The original position of the triangle is 1, 2, 3. Now after the reflection, the reflected position is 1 dash, 2 dash, 3 dash. It says reflection about the line y is equal to 0 and the x-axis is accomplished with the transformation matrix which is given below. Reflection. Now we have taken another example where the original position and the reflected position looks like the mirror image of the reflected position looks like the mirror image of the original position. Reflection of an object with respect to the straight line y is equal to x. As you can see, they have considered a line y is equal to x through the origin 0, 0. Now the original position of the triangle is 1, 2, 3 and the reflected position is 1 dash, 2 dash, 3 dash. And the matrix for this given reflection is given by a 3 by 3 matrix which is 0, 0, 1, 0, 1, 0, 0, 0, 0, 1. Lastly, shear transformation. Shear is a transformation that distorts the shape of an object such that the transformed shape appears as if the object was composed of internal layers that has been caused due to the slide over of each others. Two common shearing transformation are those that the shift coordinates x values and those that shift y values. Here is an example of shears transformations. The first diagram shows the original form of the data. Next, the second diagram shows what happens to the object when the y shear coordinates are changed. And the third diagram shows when the x coordinates are changed, that is the x shear. This brings us to the end of the presentation. In conclusion, I would say to manipulate the initial created object and to display the modified object without having to redraw it, we use transformation. Until the next time, thank you.